We now know that when we undergo a phase change, the amount of energy that's required to do that depends only on the mass of the substance that we have and a constant. When that phase change is melting, that constant is the heat of fusion. In this experiment, we're going to attempt to find that value through making some measurements. I've got a balance here. I'm zeroing it out. And now I'm going to weigh an empty styrofoam cup. I'm using styrofoam because it's a good insulator, so any energy flow will be handled inside the cup. So that was 4.19 grams. Now I have some water here, and the temperature of this water is the temperature probe that you can see. The temperature is 34.1 degrees Celsius. And after adding the water, the cup with the water in it now weighs 150.21 grams. Now I'm about to add some ice to this cup, and then I'm going to insulate it. Let's think about what we're going to do in this experiment, make a plan. So here's the strategy. As we melt this ice, energy is going to be added from the warmer water. The ice will not change its temperature because it's at its melting point. What will happen is that the ice will increase its phase energy because it's going to change from the solid structure to the unstructured liquid phase. We can quantify that, as we know, by taking the delta H of fusion times the mass, but we don't know what the delta H of fusion is yet. That's our objective in this experiment. The other thing that's going to happen is we're going to extract energy from the warmer water. This will not cause a phase change because it's still going to be water when it's done. However, it's going to be much cooler so that the energy lost is due to a loss in temperature. It'll be a decrease in E therm. When that happens, we can quantify how much energy was lost by taking the specific heat of water times the mass times the change in temperature. So let's look at both of these things at the same time. One thing that's happening is energy is going into the ice. That will cause a change in E phase. The other thing that's happening is energy is going out of the water. That will cause a decrease in E therm. But because the energy that goes out of the water is exactly the energy that goes into the ice, if our insulation works perfectly, that means it's reasonable to assume that these two amounts of energy are equal. And since we have an equation that can quantify both of them, we could set those two equations equal to each other. So that means the delta H of fusion times the mass of the ice that melts, that undergoes the phase change, is equal to the specific heat of water times the mass of water times the temperature change that the water experiences. So we can measure the mass of ice. We'll have a way of doing that. We can measure the mass of the water by just subtracting the cup from the total. And we can measure the change in temperature because we measured it at the beginning, and we can measure the temperature at the end when the temperature has reached the temperature of the ice. The specific heat of water is well known, so that leaves us only one unknown, and that's the thing we're trying to solve for, the heat of fusion of ice. So now ice has been added to the cup, and we're going to allow it to melt, and you can see the temperature of the water going down as energy flows from the water into the ice to cause the ice to melt. Melted all my ice, so I need to add a little bit more. I want to still have some ice left here. I want the temperature of the water to go down to the melting point of ice. Well, we sped that up for a while so you can save a little time. But you can see now that the temperature is not going down as quickly as it did before. It seems to be settling in at about 0.7 degrees, and I can hear that there's still ice in the cup. It's rattling around as I swirl. Temperature has dropped down to 0.6 degrees. temperature probe might be off a little bit, or there might be some impurities in the water, because this is probably the melting point of our ice. Now I have some ice that's still unmelted in here. I want to get that out of there because I want to account only for the mass of the ice that underwent phase change. So I'm going to get out this stuff that hasn't undergone phase change yet. And now I'm going to put this on my balance. So now what I'm weighing is the styrofoam cup plus the water that cooled down plus the ice that melted, and that comes out to 217.18 grams. So now let's do something with our data. Remember, this is the equation that's going to allow us to solve for the delta H of fusion, or the heat of fusion. If we divide both sides by the mass of ice, we have isolated the value that we want to solve for. Heat of fusion is the specific heat of water times the mass of the water that cooled down times the temperature change of that water divided by the mass of the ice. Here's a data table with the information from the experiment, and the equation is alongside it to the right. In order to fill in the values in this equation, we're going to have to do 3 calculations with information from the data table. First, we need to know what the mass of the water is that cooled down. Well, that's just the mass of the cup plus the water, and we take away the mass of the cup, and that ends up being 146.02 grams of water. We also need to know the temperature change. It started at 34.1, it ended at 0.6, and so our temperature change was 33.5 degrees C. We also need to know the mass of the ice. So this is the ice that melted, remember, only the ice that underwent phase change. So that's 217.18 grams. That was the mass of the water with the melted ice and the cup. And then if we take away the mass of just the cup and the water, that leaves us with 66.98 grams of melted ice. Now that we have this information, we can put it into the equation that we've created in the appropriate spots. And this is what we have. If we take this equation and multiply together all the terms on the top to get one number, it will be 20,400. And the unit will be joules, an energy unit, because degrees C and grams will both cancel. So the heat of fusion of ice is 20,400 joules for every 66.98 grams of ice. Of course, because we're scientists, we don't ever want any number in the denominator that isn't a 1, so we'll go ahead and do the division problem, and we find that the delta H of fusion is 305 joules for every gram of ice that you melt. What we found from this experiment was the value of the heat of fusion for ice. This isn't the accepted value that we find in tables or charts or on the internet. Many scientists have done this experiment many times, and the true and accepted value for this is 334 joules for every gram. We were a little bit lower than that. Possibly one of the reasons is because the temperature change might have been larger than we actually thought. I gathered the information from the temperature probe, but then I noticed later on as I was making my measurements that the temperature dropped a little bit, like another maybe degree almost. And that would make our value larger, but probably not as large as 334 joules per gram.